Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is my honor to introduce Dr. Jose Massinger. Dr. Massinger is a professor of computer science at the University of Illinois at Urbana-Champaign. Prior to moving to UIUC, he was a principal scientist in the Stanford Research Institute. Dr. Massinger has made fundamental contributions in the frontier between executable formal specification and verification, declarative programming languages, programming methodology, concurrency, and security. His work in all these areas is highly cited. The mod language is one of the most advanced and efficient executable specification languages. It supports a wide range of formal analysis, including symbolic simulation, search, model checking, and theorem proving. His collaborators and other researchers have used mod to build sophisticated systems and tools, and to specify and analyze many systems, including cryptographic protocols, executable formal semantics of programming languages, formal analyzer for conventional code, theorem provers, and tools for interoperating different formal systems. Now let's welcome Dr. Massinger to visit MSR.
Thank you very much, Yuo. It's a pleasure to be here. And what I would like to do this afternoon is to give you a little bit of a sampling of some areas in which rewriting logic, is being applied. So I will not try to be exhaustive, but I will try to give you some, general high-level overview of what rewriting logic, which is the logic underlying the mod language, is like, and what are some of the application areas in which this seems particularly well suited, and also what is the formal environment of tools around the language, of other reasoning tools that are also worth using, both to specify and to verify systems of different kinds. And I will be very happy to have a little bit of an interactive mode, if you like, so that if there are questions or things that you would like to ask as I am explaining, I'm very happy to stop for a moment and address them. And then, of course, at the end, if you have other questions, I will also be very happy to answer them. Hello, Ambarish. Good to see you. So rewriting logic is a very simple computational logic that is I think, well suited in the experience that we have accumulating over the years to be used as a semantic framework in which you can express many different modes of computation, including many modes of concurrent computation, many different kinds of systems, of programming languages, and at the same time, rewriting logic is like a coin with two sides. One side is computational, the other one is logical. So the same reasons that make it a very expressive semantic framework to express all kinds of computational systems makes it also a good logical framework to be used as what you might call a universal logic, in which you can express many different logics and their inference systems in a natural way. And you can use then this logical framework to mechanize these logics and obtain tools for them. And we have done that. We have done both things. And what I will do in this talk is to introduce basic concepts and about the logic, and then to focus on some recent research directions to give you a little bit of a sampling. So not try to be exhaustive, but give you some areas. So first of all, extensions of the logic to model real-time systems and probabilistic systems. So you have the core rewriting logic formalism, and then extensions of this formalism, which can deal nicely with real-time and probabilities. And then some application areas such as semantics of programming languages, security, and bioinformatics. So I think a very good question. So if you are trying to push, a semantic and logical framework, in some way the proof of the pudding is in the eating. And so the question is, how good is it in terms of how expressive, how general, what kinds of problems you can naturally express, what kind of problems, you might express, but it would be a mess, so that then, it would, not be very helpful. And how can you extend it in new directions? So on this whole thing, what we have been doing is just to try to push the envelope and see, well, can we do this, can we do that? And then accumulating experience. And up to now, in general, the experience has been quite positive. And I will, in particular, discuss these two extensions to real-time and probabilities to show you how they are naturally, the formalism can deal with that. There is another feature that is useful, which is reflection. So this logic can express its own meta level, and this is a very practical thing because we can use it, for example, in the process of building reasoning tools. The reasoning tools are really manipulating not only formulas, but also they are manipulating theories in which the formulas, have to be true or not. And in the reasoning process, you may be both, a step of reasoning may change both the formulas that you are looking at and the theories that you are also using. So, for example, imagine that you have a implication elimination kind of step. Well, you should think of that as a pair of the theory and the formula, the implication. And then in the implication elimination, you move it to a new theory in which you have added the assumption as a new fact in your theory, and then you're trying to prove the consequence, for example. So by reflection, this becomes very easy to do, and I'll say a little bit more about that. And then I'll also talk about theoretical extensions of the logical framework to deal with real-time and probabilities. And then, of course, at the practical level, so this all may be very, very good and interesting from a theoretical point of view. The question is, the practical level, you have to ask questions like, how well is this formalism supported by tools? What are some application areas where this, is useful and can deal with interesting cases and so on. So I'll give a brief overview of formal tools of a tool environment that we have built around rewriting logic and mod, and how we use them for verification. And then I will focus just on three areas: semantics of programming languages and formal analysis of programs, security, and bioinformatics. If any of you are interested, tomorrow I will give a much more focused talk at 10 o'clock just on security, so for those of you who might be interested.
So that talk will be in 112-3377, 112-3377, 10 o'clock.
So let me just tell you what a theory in rewriting logic looks like. It's very simple. It's a triple where the first two components define a typed equational theory. So sigma defines the types and subtypes and function symbols that you have, in your language. And then E is a collection of equations which might be conditional. They can be conditional and unconditional equations. And so that's the first component. And then the first two components is just an equational theory. The third component is a collection of rewrite rules. So T and T prime are terms or expressions in this signature sigma, and the rewrite rule is a rewriting from any instance of this expression to any instance of this expression. These rules can be conditional. So here I'm just giving an unconditional rule, but it could be if some condition holds. So a condition or a guard, if you want. So, so that's the formal definition. But what are you specifying when you give a rewrite theory? What are you talking about? Well, what you are talking about computationally, as I said, there are these computational and logical points of view. Computationally, what you are doing is to specify in a mathematical way, which at the same time happens to be executable, provided the theory satisfies some minimum executability requirements, so you can execute it in mod. So you get an executable specification of some kind of system, possibly concurrent. And that system has statics and dynamics. The statics has to do with what are the possible states of my system. What are they? So that is answered by the equation of theory. And it says, well, is you define an algebraic data type associated to the equation of theory by initial algebra semantics. And so then any state will be a state that is an element of this algebraic data type. And then now the question is, what are the dynamics? The dynamics are given by the rules. So a collection of rewrite rules that tell me how pieces of my state can change, not necessarily the whole state, but even some pieces of it can change concurrently. And then the logic will be a logic to reason about, well, if these are the basic changes, what are the general concurrent computations that could happen in my system? So let me give you a simple example of this, just to kind of ground in some way the intuition. So here is, in the syntax of the mod language, a rewrite theory which is describing a simple fault-tolerant communication protocol. And so the main top operator is this one, in which the bracket on the left is the process that is sending data. I'm sending a list of natural numbers, and the communication is asynchronous, so I have to ensure that they will arrive in the order in which they were sent. This is the state of the receiver object, and then in the middle there is a soup of multi-set of messages in transit from the sender to the receiver. It's a channel, but it's a channel which is not a FIFO channel. Is an asynchronous channel where things could be in any order. And then you form lists by an associative operator with the semicolon operator here, which is associative. So operators can have axioms like associativity and commutativity, or associativity and identity. And so then the rewriting will happen modulo those axioms. And then you have messages like this, where you have send a piece of data and a counter saying, well, this is item number 7 that I send you. And then there's also an acknowledgement message to acknowledge that message number 7 arrived or something like that. And in this case, you just have 4 rewrite rules describing this asynchronous.
Let me try to interpret this to see if I understand it is correct.
Right.
So the 5 elements, the operation.
This operator here
this one
is the top of the state.
Yeah. So you model the sender, the receiver, and the
channel.
The wire.
The channel.
Okay. So message in the wire.
Yeah.
Do not have any order.
No. Exactly.
But
so maybe it's maybe it's a wireless communication or something like that. Right?
Yeah, but sender and receivers they
have order, so they have buffer. They have a buffer and they have data in a particular order.
Yeah. So
and you would like the communication to be received in order. So if you're sending a list, then you should get back, you should receive the
This is very similar to, for example, DCP, where you have a sequence number.
Right, exactly. And so the idea is that, this is just a very simple little example that fits into transparency, but we have, specified very complex network protocols, cryptographic protocols, things like that in this kind of way, where you just essentially say, well, and here I'm showing a very monolithic kind of top-level structure, but in general what you would want is to have a much more distributed thing where you would have different objects, and then the multi-set structure would be at the top, and then they are sending messages to each other. You don't have to have a single sender, a single receiver. You could have, and the connectivity could be dynamically changing. And here just picking a very, very simple-minded little example to illustrate the ideas. And so here you have a signature, which is the operator declarations. You have equations, and you have rules. The equations are actually implicit in these declarations, equations of associativity and commutativity and so on. And then the rules are these ones, which are really transition rules in your system. And there are just 4 rules. This is the rule for sending data. This is the rule for receiving data. This is the rule for receiving an acknowledgement. And this is the rule for losing messages. So let's begin with the losing messages rule, which is the easiest. So these are mathematical variables. So this is the state of the sender has a list of data to be sent and a counter. Here there is the channel, and here is another list of messages received on another counter, of integers received on another counter. And here you have the channel, and the idea is the channel is is a set, or a multi-set in fact, of messages, and S stands for a set of messages, and MSG stands for a single message. So you can pick any message, because this is associative and commutative, so this could be any message in the soup, could just disappear. And so that's what this rule does. So this is message loss.
A message loss without changing both counters.
Exactly. The states of the sender and the receiver don't change, but the state of the channel is such that the message can be lost. Okay? So that's just, yes?
What is the operator between MSG and S?
It's just empty syntax. So I define, so these underbars are for the arguments, and then you can have whatever syntax you want, including empty syntax, just juxtaposition.
But it's actually the union.
Yeah, it represents the multi-set union. Okay. But I represent it as empty syntax. So a set of things is just a bag with no syntax in them. Just put them together. But the order doesn't matter because it's all associative and commutative. And then in the sending, for example, L is a list, a variable defining a list, and J is an integer. So this is the first thing in the list, and then this is the counter, and then this is the channel in the middle and the receiver, and then you just inject the message J counter N as a message, and you still keep it there because you have to wait for an acknowledgement. Okay. Then in the receiver, if the message has the appropriate counter, then it will be put in the buffer, and if not, it will not. And then in any case, an acknowledgement is sent back, and then when the receiver gets the acknowledgement, if the acknowledgement corresponds to the counter, then it can drop this thing and then move on to the rest of the list, and then increase the counter. Okay, and if not, it cannot. It still has to wait. Okay, so that's just a very simple example of this general idea, where you have again the signature of operations with types and subtypes, some equations and some rules defining this concurrent system, for example, of this channel. So this is a concrete example just to ground the intuition. Any questions on the example?
This looks very similar to abstract state machines, right?
It has a similarity and a similar, in some way, goal in that both abstract state machines and rewriting logic aim at giving you executable specifications.
Right.
But they are different semantic frameworks. So that, here we do it, with this, equational definition of the statics and then rewriting for the dynamics in the abstract state machines, you have in some sense the idea that they were originally called evolving algebras, in Yuri Gurevich's. So the idea there is that you think that you have a mathematical model as an algebra, and then when you make a change of state, then you have another mathematical model in which something has changed. So that's a different kind of semantic. Here we have a single mathematical model for all the states. And then within that single mathematical model, then the changes correspond to these rewrites, possibly elementary, possibly complex ones, which correspond to proofs in the logic. So the idea is that here computation becomes deduction. So concurrent computation becomes a proof in the logic, as I will illustrate in a moment. So philosophically, the goals are similar, but the way those goals are achieved mathematically are different.
Instead of having a sort of a Kripke model where you change your assumptions, you have one static model. Is that?
Well, you can associate to the initial model of the rewrite theory a Kripke model.
Right.
So in which the states will be the states of your Kripke model, and then the transitions will be the rewrites. And then, of course, you can, on top of that, so MOD has, for example, a model checker for linear temporal logic. So then you can do model checking, for example, for that. So the mathematical model associated to the rewrite theory is essentially a Kripke model, and you can systematically associate to it a Kripke model if you make explicit what predicates you want to model check, which you could define equationally as predicates. So any other questions on this part? Okay, so let me continue then. So it has a very simple set of inference rules, and rather than going through this somewhat boring syntax, I'm going to show the inference rules to you. So there's 4 inference rules: reflexivity, equality, congruence, and replacement. 5, and transitivity, excuse me. But let me visualize them for you. So first of all, what are the inference rules talking about? Well, the inference rules are inference rules in which you can infer from elementary concurrent transitions what are the general complex concurrent computations that you could have in your system. And they are exactly the ones you can prove in the logic. And so each inference rule corresponds to reasoning about what concurrent transitions can I have. So the first concurrent transition you can have is identity idle transitions where nothing changes. So you say, well, that's reflexivity. So if I am in a state, by doing nothing, I remain in the state. The second one has to do with combining the equations and the rules, and tells you, well, look, my states are not syntactic things. They are really elements of an algebraic data type. So anything that is probably equal by the equations is the same state. So if I have a transition on any term representation of the state, and this other is another equivalent representation, then I also have a transition there. Okay. In practice, what we'll do is go to some canonical form by the equations and then do the transition in the simplest possible description of it. But mathematically, this is what the equality rule tells you, that your transitions are not on terms, but on equivalence classes modulo equations. The third rule is a rule for what I call sideways parallelism, which is the normal way parallelism happens. And the idea is that, well, you don't need to have any specific parallel operator. Any operator becomes a possibly parallel operator. Yes?
It's just maybe an implementation question, but when you define your rules, you could sort of separate equivalent states, like saying, for example, if I take the first message in the set, then something happens, and if I take the last message in the set, something else happens. Whereas that shouldn't be true, right? I mean,
well, so if you
mess up the rule by when you define your trust.
I think you have a very, well, it's more than an implementation question. Is if I understand correctly,
Right.
and you will tell me whether I do or not, if I understand correctly, you're asking about the executability conditions for a rewrite theory to be nicely executable.
Well,
Because,
how do you know this?
no, so let me go back to the picture, because this is the key picture. The rule, you're really talking about this problem here.
Yes.
And so what you are really saying is the following. Suppose I am applying the equations as simplification rules. And maybe before I simplify my state description, I could have taken a transition. But how do I know that I can now computationally be able to know that I can take the transition here? So we call that property coherence. It's a coherence between the rules and the equations. And what that means is that and we have a tool to check that. And so the idea is that then we don't have to worry about it. We can just go to the canonical form, and then we are guaranteed that any transition I could do before, I can do now. This is very important, for example, for model checking, because if you don't have that property, you will not explore all the states. There will be a space that you are missing. And then your model checker will say that your property is true, but really maybe it's not, because you gave it a specification that mathematically was okay, but computationally wasn't. Because the issue is that, this equality here, you see, in general is undecidable when two things are equal. So we are assuming that the equations are Chern-Rosser and terminating, modulo things like associativity or whatever. And furthermore, we are assuming this coherence. So then so we are doing something quite sophisticated, which is rewriting equivalence classes, but then becomes decidable under these conditions. So the equations can be whatever you want, but provided that they are Chern-Rosser and terminating, and provided that you have this coherence, which you do some kind of critical pair checking, then you're fine. And this is, of course, a requirement. So your question is very insightful, and I think I understood it, right? Yeah. Okay. So congruence is sideways parallelism, but not to any fixed operator, but any operator. So your state will be built out of some constructors of whatever kind, and then parallelism means that I can rewrite different pieces of these. So whatever f is, I can do that. And then replacement is a different kind of parallelism that is not so well known, which I call parallelism under your feet. So imagine you have a firewall. Maybe inside the firewall you may have a whole subnetwork. And so maybe there will be rewrite rules that negotiate security checking to enter the firewall. But underneath that, all kinds of computations can be happening in the subnetwork. So this is reflected here by the fact that you can rewrite from T to T prime with a rewrite rule, but in an instance of this pattern, there may be a whole bunch of things below in which you could also be doing other rewritings. And so the most concurrent description of the thing is that you should allow not only rewritings sideways in different pieces, but also the nested rewritings that could happen at different levels. Okay? And so this is captured by a rule of replacement in which we allow you to apply a rule not only here, but also below. Of course, these two together allow you to rewrite in any context, because by applying congruence inductively, this could be happening not just at the top, but anywhere. So combining congruence and replacement, you allow any rewriting in any context, but furthermore, you allow nested rewriting. So in general, then the parallel rewrites that you can have could be both sideways and nested. And then, of course, the last thing that you're lacking is transitivity, which says that you can keep going. You can, have, if you can do some complex rewrite from here to here and here to here, then you can just sequentially compose them and so on. So then computation and deduction become the same thing. So a concurrent computation is something you can prove it, and something you can prove it corresponds to a concurrent computation. Yes?
Mark, on the previous slide, the picture
kind of suggests that congruence is just a special case of replacement. If that's not the case, then you might think of a better picture, maybe.
Congruence is not a special case of replacement. So the idea T and T prime are, this is a rule. So you have, if T rewrites to T prime,
So F rewrites to F.
well, you would need to have a rule for that.
Did you have reflexivity?
Yes. So reflexivity is true, but then these are only sort of zero-step rewrites. What they allowed you, so in reality, combining congruence, replacement, and reflexivity, you can rewrite anywhere in one step. So congruence really means you can build any context. Now, this is really rewriting at the top with the rule, and in the most simple-minded way, you would just not rewrite below. So you would just have T rewrites to T prime if T rewrites to T prime is a rule. But we want to give the additional, or say any instance, but then you wouldn't change the instances. But to increase the parallelism, then you say, well, I allow you a proof here. If you give me proofs for rewrites in the substitution, and also this is an instance of my rule. So inside the way you could give a different equivalent set of inference rules. The particular motivation of this choice is to maximize the parallelism, to have inferences that in some way give you the most maximal description in which both the side weights and the nested parallelism can be reflected. So that in one step of parallel rewriting, you can have both kinds of parallelism happening. But if you go to an interleaving description, you could have simpler things, and you could have just, say, a context rule. So you could have a more simplified thing that, for an interleaving point of view, would give you the same interleavings, but from the point of view of expressing the concurrency, it would be more limited. Is that sufficient? Yeah. So let me tell you briefly about reflection. So we have shown in work with one of my former students, Manuel Clavel, that rewriting logic has a nice way to represent its own meta theory, its own meta level. And the way this happens is that there is a finitary theory, a finitary rewrite theory. In fact, there are several of them, but you can find theories that act as if rewrite theories were to be Turing machines, then this would be the universal Turing machine. So it's a theory whose deduction can simulate the deduction of any other theory, including itself. So what that means is that if I have here a theory and I can prove that T rewrites to D prime by possibly many rewrites, concurrent rewrites, then this will happen even only if in the universal theory I can prove that a term that represents R and T, where R now is a data structure, can rewrite to a term that represents R and T prime. And then you can iterate it because you could then reflect U itself and so on. Now this is theoretically quite nice, but it's also practically very useful, and we exploit it a lot in mod. One way in which you can exploit it is to define rewriting strategies. So your theory may be highly non-deterministic, and it could go in many different ways. So by reflection, you can write rewrite rules one level up that guide the application of the rules one level down. And so you can write different strategies like that and have strategy languages to explore the highly non-deterministic kind of behavior of your system. The other thing you can do is to efficiently implement the reflection in a built-in way, and there's a modular mod called meta level, because you could think, well, to simulate one step, what takes me one step of computation can be a huge mess, one level up. So this may be highly inefficient. But what we do is to look at this equivalence, which we have proved, and to use it in this direction. So when we are doing a meta-level computation, a anytime we have a situation like this, we can break it down to ordinary rewriting below. And then what it means is that we can do any meta-level computation with the same efficiency, essentially, as the corresponding object-level computation, except for two changes of representation which are linear in the size of the thing at the beginning and at the end to change the term representation. So in fact, this reflection is actually very efficient. And so then we can build theory-improving tools using reflection, as I was explaining before, because you can carry the theory and the formulas, and then you reason about this pair, you know, in the thing. And you can also, using theory-improving, theory-improver mod, we can also use it to prove metalogical properties. So we can represent a logic, like, say, logic of implication, as where each inference step corresponds to an inference, to a rewrite rule, and then prove things like the deduction theorem or things like that as properties of the initial model, you know, for the theory that we have represented. So this is the use as a logical framework. Yes?
So I don't quite understand this part, but I think are you saying that by reflection you can add rules to change the underlying behavior of mod?
Well, not quite. What you can do is that you have the original mod specification, you know, given by a module, by a rewrite theory. And then you can have rules one level up that manipulate this theory, for example, to guide the deduction. So maybe the deduction could be highly non-deterministic, and you want to give certain preference to say, well, first rewrite with these rules, and then after that rewrite with these other ones, or whatever, right? So any deduction that you will do this way, guiding at the meta level, will still be a correct deduction below, but it will be guided. It will be guided, right? So that's what. However, what you are saying is also true in a different way. In addition to having rewrite rules that guide a fixed theory, you could say, well, I want to have a system where my code changes dynamically. So then what you could do is to have rewrite rules where the theory, which is the code, can be changed dynamically to another one. So you could adapt dynamically your code to be something else. So that also can be expressed at the meta level. But then it would not be a computation that corresponds to something below. It would be something more general, in which you are, you know, changing your system as you are executing. So adaptive, you know, behavior of that kind can be done, you know, in that way, which I think is the kind of thing you were thinking about.
Yeah, I was thinking maybe, but I think this may be wrong. I was thinking that an analogy is that you can always use a C language to implement a C compiler, but I guess this is wrong.
Well, it has something to do with that, in the sense that it's not entirely inappropriate. So let's go back to the universal theory here. In some way, you could think, it's a little misleading, but you could think of you as a metacircular interpreter, in some sense. So is an interpreter to execute rewrite theories in the logic itself. Okay? But it's highly non-deterministic one, because, you know, it doesn't, you know, for a functional language, the metacircular interpreter will have an eval function and will just do a single thing. But here, these rewrite rules can go in many different directions. So this metacircular interpreter is doing rewriting in many different directions to see whether they can find a proof in here. So in that sense, it corresponds computationally to implementing the language in itself, so to speak. So let me tell you a little bit about the formal environment of mod. So, what can you? So, suppose that you specify this communication protocol I gave you. What can you do with it? Well, you can do several things. You can, first of all, you can execute it, and so you can simulate your protocol and see whether the behaviors you're getting, are okay. And in mod, you have some built-in strategies, which, for example, give you a fair computation. So, fair in which all the rules will be applied, and also you are position fair, so that all positions in the expression will be rewritten eventually. And if you have objects, you can even be object and message fair, so all messages will be given a chance to rewrite and so on. If you can represent object systems very naturally here. So you have a fair execution, and you can see what happens with that. And then maybe you realize that your specification is wrong. This may be a design for a new protocol. And in fact, we have worked with people in networking who have found this useful to explore new designs of protocols before they implement them in C++ or whatever, and so find all kinds of design flaws in their thinking before they invest the effort. And then you have an executable model that's very easy to give to a graduate student, and they can implement it in C or whatever. So you can do this simulation. The next thing that you can do is suppose that you have an invariant that you would like to hold. Maybe you would like, not in this protocol, because this will terminate, but it's not something that it's like kind of, it's always doing something, it's always reacting. You want to make sure that you are deadlock free, that you don't have any deadlocks, for example, or that some predicate corresponding to an invariant holds. Then what you can do is we have a breadth first search command in mod, which can be relative to a semantic condition. So you can search for a reachable state where some predicate holds. So what you do is you take the negation of the invariant and search for it. And if the system fails to satisfy the invariant, you are guaranteed to find a state in which this fails. If the system, we also have a bounded search where you can give a bound, and then you do bounded model checking in some sense for that. If the system is of course infinite state, then if the invariant holds, you'll be searching forever for a counterexample, and you will not find it. But we also have abstraction techniques where we can then, by giving, for example, more equations, we can collapse the state space into a finite one, and then the search will, of course, terminate. So that's the first thing you can do. The next thing you can do is, if the number of states reachable is finite, then we have a linear time temporal logic model checker built into mod, which has efficiency comparable to a spin. In fact, Amberich there did some of the first experiments comparing with the spin, and then we have done other experiments later on. And so it's an explicit state model checker for linear temporal logic. And then you can model check any linear temporal logic property. And in addition, we have a tool environment with other tools. We can check for the equational part whether things are Rosser. We can check for termination. We can check for this coherence that came up in your discussion. We can check for something called sufficient completeness, which is if you are given an equational definition of a function, have you given enough equations, or are you missing cases? And then we have a decision procedure that will give you a counterexample if you didn't give enough equations. We have a prototype tool to do predicate abstraction. And then there are tools for, there's a very nice tool for real-time systems that I will tell you in a moment. And also another tool not included here for probabilistic systems that is in prototype stage at the moment, but I will also tell you about that. So I'm now going to move to different applications and different extensions of this. So the first thing I want to tell you about is a project involving a number of people in Europe and in the US. But in the US and in Illinois particularly, Grigori Rosu and myself, with a number of students. One of them, Fen Cheng, has been here actually as a summer student sometimes. And Asadeh Farsan, who was presenting a paper on atomicity at CAV, this past few days, is also another student. So, and then a number of other students at Illinois. So we have been saying, well, how good is this as a semantic framework to define semantics of programming languages? And essentially, our experience there is quite good in that, in some way, this distinction between equations and rules in some way allows us to combine the best of the notational semantics and structural operational semantics. So if you think of rewriting logic compared to those two ways of defining semantics of programming languages, the notational semantics is everything are equations. There are no rules. And furthermore, is really well suited for sequential or deterministic languages because you assume to have the Church-Russell property. If you go to SOS, everything are rules. And you can deal with concurrency and so on. In our case, the semantics of Java, for example, we have done all of Java except for the libraries, all of the JVM, and a whole bunch of other languages. The semantics definition will be a collection of equations for the deterministic part of the language, those features that are purely sequential, and then a collection of rules for the thread interactions. And we have, in some way, a dial where you can be more or less abstract. So the most concrete version is that you make everything into rules. So that would be like SOS. But then you have many more states to explore. The most abstract version is one in which any deterministic feature is expressed with equations. And then only the things that are non-deterministic and concurrent are done with rules. So for things like Java, the JVM, we have typically hundreds of equations. Typically, you have just one or two equations of rules per feature, like if then else or whatever. So we typically have hundreds of equations. For the JVM, we may have something like 350 equations and about 40 rules. For Java, we have hundreds of equations and maybe 20 rules or something like that. And what this buys us is a huge power of abstraction or state space reduction. Because any sequential subcomputation of a thread, we only see the canonical form of the final result. And then when there is a real concurrent interaction, we can, of course, you want to be more detailed, you could, use more rules, turn more things into rules. So we have done comparisons with Java Pathfinder and with the Java model checker of David Deal at Stanford. And for a number of common benchmarks, we typically are faster. Even though it sort of sounds ridiculous because you're taking a semantic definition and then using it as a tool. So it sounds like, how could you possibly hope to do something that competes? But it actually does. And the secret, I think, is in this abstraction. So the fact that the distinction between equations and rules, gives you a massive reduction in the number of states. And then this is, you could think of it as transactions in some sense. Is that any kind of thing that you can do with equations is like a transaction, in which you just go to the final result of that transaction. So then again here the idea is that once you have the semantic definition, you get automatically an interesting set of formal analysis tools for the language in question. We have also added partial order reduction to that. So we have a way of doing partial order reduction in a language generic way. That's also work that Asadeh and I have done. And then, this is now, in programming languages courses at Illinois, this is students as term projects, define semantics of entire languages, maybe not 100% of the language, but interesting subsets of them for, all these languages, for example, have already been specified that way. But the place where we have, in some way, had the most mature, full specifications are Java and the JVM at the moment.
Thinking, for example, for operators like your union operator, the one without, before applying an equation, you need to find a sort of matching. You have a word problem, for example.
Well, we have matching algorithms modulo any combination of associativity, commutativity, and identity, which are very efficient.
But this is the word problem, right?
No. No, it's decidable. So matching modulo associativity, commutativity, or identity is decidable.
And the three of them?
The three of them, any combination. So any operator can, so if you look, for example, at here, if you look here, this operator, the set union operator, is associative, commutative, and has null as an identity. And this other one, list concatenation, the append, this append, is a constructor, and is associative and has nil as an identity. So when we apply equations of rules, we are rewriting modulo these equivalence classes in a built-in way, which is decidable, and furthermore is efficiently implemented. So for commonly occurring patterns, we can do a step of rewriting modulo associativity and commutativity in time logarithmic on the size of the term that you are matching. In the case of associativity, we can do it in constant time.
Yeah. So I could write, for example, the pattern in the antecedent of one of those rules.
Right.
For example, like the last rule.
Well, this is a pattern here. For example, this is the pattern modulo associativity. And also an identity. For example, imagine that I have only one number.
Yeah,
And then and nothing else. Then L will grab the identity. And this will match also a single number, for example.
yeah, and when you add, I'm not sure, but I think when you add commutativity there, like in your last
Yes.
rule,
Yes.
if
So,
instead
yeah,
of-
for example, this one, yeah. So this is matching modulo commutativity. This could be anything.
Yeah, sure, but this is just one atom.
Any message, yeah.
It's
And-
one atom, but
yeah.
what if I had 2 or 3, let's say 3 sets there? And
So suppose that you have 3 elements, and suppose you are doing model checking.
yes.
So then there would be 3 matches for each one of the elements.
No, I don't.
And then there would be 3 transitions.
Yes, I know, but I don't mean individual elements. I mean, if you have in your there, I say instead of message S, I said S prime. Let's say.
Yes, so then you will have all the possible partitions
Yes.
will correspond to all the possible rewrites.
All the possible partitions with all the possible orders.
Yes.
Isn't that?
Well, no, but modulo the orders. The orders are already modulo. So any
Yeah, but
decomposition
in your
into a set
representation,
into
you can- in your representation, you have to choose an order.
no, we have internally each multiset has a unique representation.
Okay.
So this is not done in the dumb way; it's done in the smart way.
I guess.
And there are red-black trees that make this thing very efficient. So essentially, in practice, what it means is that we can do millions of rewrites per second in the case where there are no axioms, and we typically have a factor of 10 hit if we are doing rewriting modulo associativity and commutativity and things like that. So go it down from millions to hundreds of thousands per second. But of course, you are doing something much more sophisticated. It's like a symmetry reduction in some sense. So this is quite lively. So I am a little bit, well, we started a little bit. So, but maybe could I have a little more time to continue and so on? Yeah. So let me tell you briefly about real time. How do real time systems show up here, and also about probabilities. So intuitively, well, imagine a system where time passes for the whole system. So one way to express that it passes for the whole system is to have an operator like this curly bracket that grabs the entire system. Then the system could have pieces to it, but the passing of time, the ticking of time, there could be rewrite rules that happen inside that are 0 time, but the rewrite rules that correspond to advancing the time should in some way happen for the entire system. And you can then think of a time advancing rewrite rule as a rewrite rule that rewrites t to t prime if some condition holds, and then in an amount of time r, which could be in general not a constant but an expression, depending on time. So that way you can represent a real-time system as consisting essentially of 0 time rules, where r here would be 0, and where you then need to rewrite the entire thing but a piece of it, instantaneous 0 time rules, and then tick rules that advance the time. and many different real-time formalisms, time I/O automata, or time Petri nets, or timed automata, or hybrid automata. All these things are special cases of rewrite theories of this kind. Now the question is, how do we do that within the logic itself? So the way we do it is by interpreting these rules as rewrite rules of a pair where we have an explicit clock. And so here is the state, and here is the time of the clock, and then the rewrite rule, if R was the thing here, the rewrite rule will include the clock by R if some condition holds. So that's the way it goes. And by using this representation, this is a faithful representation, so it's if and only if kind of thing. And then we can compute, specify, and reason in mod about real-time hybrid systems. And there's a tool called real-time mod where this is very efficiently supported. Now, there are some interesting issues about completeness, because what happens if you have dense real-time? A tick rule now could go to an infinite number of possible states in the middle for any choice of time. You couldn't possibly visit all those states. So what do we do? What we do is to visit relative to a time increasing or ticking strategy, where essentially we tick to the next instant where something interesting will happen, where some zero-time rule will become enabled. Now the question is, and then we can do model checking of any linear time temporal logic property, which may include properties that look at the clock. So in practice, we can be very expressive without the logic having to change. We can really deal with real-time properties. So now the question is that your model checker now, if it comes back and says true, then what you know is that it's true relative to the states that you have visited. What happens with the other ones? So we have, Peter Olbesky and I have proved a general result showing that under very weak assumptions that happen to hold for practically all the examples that over the years we have been exploring, you are complete. And these assumptions are easy to check and are very mild. Essentially what they say is that the state predicates are not changing arbitrarily in the middle between one place and another. They change at most once. When you are ticking to some next time that you are enabled, the properties are not going to be changing, all the time, because then of course, and then in practice, in most normal systems, that's the case.
Why is it different from time model checkers like UPAL? It's not.
Oh yeah, there's a huge difference. There's a huge difference because what you can represent by a time automaton is very limited. So imagine you have, a network protocol in which you are creating new messages, there are new nodes that can be created or whatever. There's no way you can represent that as an automaton because you have to know how many states you're going to have, okay. Right? So the difference here is that, there are decision procedures for very restricted formalisms, and then there's nothing, right? And so here, what we can do is to have, very flexible way of specifying, all these kinds of things like wireless protocols, active network protocols, scheduling algorithms which have data structures that are unbounded, things that you couldn't possibly specify in UPAL, and then still be complete for our analysis.
And time automata would be just a special case of this.
It's a special case, but it can only express what it can express. And of course, there you have decision procedure. So you have this tension between desirability and expressiveness, and we are kind of in the middle. Yes.
You mentioned some restrictions on that when you apply a rule at a particular time that you don't apply it many times or so. Do you actually check those, or do you check also for like Zeno properties?
Oh yeah. So this is relative to non-Zeno behavior, and And the other requirement is that, we will jump to the next moment when something becomes enabled. So the question, the key question to ensure the completeness is, are the state predicates changing a lot in between?
Right.
So if they're changing a lot in between, then the completeness is lost.
Right. I see. Yeah.
If they change only once, not necessarily at the end, but sometime in the middle they change once, then you are complete.
Right. And do you check that the system that you're given, that the equations that you're given, that they have that property?
So we have semantic conditions that are checkable and easily checkable that guarantee the property. And for all these examples, they actually satisfy the property. So it's not a property that, it's nice to write a paper, but then in practice, you couldn't use it. A posteriori, because this is more recent work, we have found that all our analysis for all these kind of complex things do satisfy these requirements. So the requirement is practical. And there is one limitation that I should mention, which is that this decidability and completeness is restricted to bounded temporal logic properties. So meaning time bounded. So we can be complete for properties of the form. This temporal logic formula holds, up to 300 seconds. With this time bound.
Not like Ihi automatons where you stay in one state forever.
No, so you go up to a certain amount of time.
Yeah.
So for those, but many properties are very useful like that. So for these time-bounded properties, and under those conditions, this is the decision procedure. I'll now kind of go a little bit quickly because I don't want to kind of abuse your kindness and patience. So let me just tell you quickly that what do you do for probabilistic systems? You have rigor rules which are non-deterministic, meaning that you can have extra variables on the right-hand side. So what you put in y, you don't know. But so this is a non-deterministic rules where you don't know what to put in these new variables. But what you put there is chosen by a probability distribution. Okay? So let me give you a very simple example of that. Just to ground the discussion, imagine this watch I have here. So it has essentially one rigor rule that ticks to the next second, but it has a battery. As the battery runs down, at some point, the clock dies and I have to go and buy a new battery. It actually happened a few weeks ago. Okay, so you can model that by saying, well, I have a tick rule, so I can represent the clock as the time and the amount of battery, the amount of charge in the battery. So if everything goes well, I tick to the next instant and I decrease the battery by a little bit. But it could also go to a broken state. And what is the new variable on the right is this Boolean variable b, which is an if then else. But the value of true or false there is chosen probabilistically according to a Bernoulli distribution, but it's not a fixed one. It's one that depends on the charge. So as the thing is ticking, the distribution is changing. The bias of the coin is changing. So that means that the variables on the left-hand side of the rule, I have a parametric family of distributions, and then depending on the variables on the right-hand side, then the bias of the coin will be different. This is a discrete thing, but it could also be continuous time or whatever. And so we can, in this way, model all kinds of more probabilistic systems, both continuous and discrete. And furthermore, we can do statistical model checking, and we have applied this. Tomorrow I will talk about how we can analyze denial of service protocol, persistent protocols using a statistical model checking relative to these probabilistic systems. And then there are security applications. I will talk more about that tomorrow because I don't want to keep you here. And then I will just very briefly give you some kind of, I'll talk in words and I'll show you one rigor rule to give you an idea, in fact, this is a work that started when I was at SRI with a couple of molecular biologists and with Pat Lincoln and Caroline Talcott, and which has continued, very nicely at SRI. And Caroline, in fact, gave a talk. There was a workshop on bioinformatics, and she gave a talk on the most recent work there. So the idea here is that, well, you can develop mathematical models of cell biology, and I think there's work by Luca Cardelli in the same kind of spirit, for example, at Cambridge. So you can develop models of cell biology symbolically by saying, well, a cell is some kind of data structure, is some kind of nested collection of soups, of soups of proteins. So it's really a bunch of sets in between these membranes. And then a molecular biology reaction is a rewrite rule that rewrites some proteins to some new other proteins. And then I have, a mathematical model of the cell biology, and then I can analyze it, analyze pathways, for example, chains of reactions that would lead to interesting things, and so on. You can also, if you want to add probabilities, then you would make the rewrite rules probabilistic. Okay? And so this gives you mathematical models at a high level in which you can, reason about cell biology. Furthermore, since the data reported experimentally is not always consistent, you can even have several models in which you have, different, say, well, if this experiment is the right one, then I should see this kind of behavior. So you can even discriminate between different models and so on, and have a loop to suggest experimentation and things like that. So I'm going to just go to a single rewrite rule and illustrate it without, tiring you much more on that. Which is this rewrite rule here, which I will explain, what it looks like. So I am representing the cell as a bunch of nested soups. So the top level is this curly bracket, which ends up over here. And then in the cell membrane, there's a soup here. So inside the membrane, it has two walls, and there are proteins in the middle. Then you have another soup for the cytoplasm, and then another membrane for the nucleus, if you have a cell with a nucleus, not for the bacteria, with another soup inside. So this is the soup in the cell membrane. This is the soup in the cytoplasm. And I am not directly representing the nucleus, but I could. And this is in a survey on biopaths, this is a particular reaction that is described here in English. What it really means is the following. So these are proteins. This is an operator to connect proteins into complexes. And this is an associative commutative operator says, well, if in the cell membrane I have this complex of RAS and GTP, and whatever is the rest of the soup here, and if inside the cytoplasm I have this other complex in which there is phosphorylation, which corresponds to energy, then this whole thing is going to move into the membrane, which is what happens here. So you can have rewrite rules that happen inside a given soup, but you can also have rewrite rules that cross boundaries, where pieces of the proteins move from into the membrane or out of it, and so on. And this happens to be a membrane crossing kind of rewrite rule. And so again, you can use all the tools of model checking and so on. And they have also even special purpose tools, and they have developed in this project also graphical descriptions where biologists can see pictures and so on, which is what they like to see, to interpret the thing. Yeah, and so I have just given you a little bit of a sample. There is the companion paper here of this talk that I will leave with Shuo, so if anybody's interested, you could get a copy of the paper. And there is another theoretical computer science survey paper, which appear in the reference of this companion paper. Mod itself is freely available. in this, at UIUC, in this net address with the sources and documentation. And we're just about to ship a book to Springer in mid-September, which has many examples, explains the language, the theory, the applications, and so on. Thank you very much for your interest.